What's up, everybody? Welcome back. Day 17. If you've been following along, we just uploaded day 16, so we're in a hurry. It's late. We're trying to get it done. We got a little behind. So day 17, before we jump into it, I want to give you a little tour around the project that I've got set up for us so that we can just cruise right through. So I've just got the function for day 17's part 1 and 2 stubbed out. Now the other thing that we're going to use is, I've got this right here. This is something that just comes up in Advent of Code so often that I figured it's time I finally have an extension for it. What this is an extension on array when it's an array of characters. What this does is it makes it so that we can actually go through and we can find the coordinates. So let's say, for example, so let's say we got an array of strings, or an array. Let's try saying that one more time. An array of characters. This is super common because you get like you'll take like the lines of an input, and let me show you right here. So you have something like this. So each line would be an array, and then the whole thing would be an array. And this kind of a setup shows up so often in Advent of Code that I thought we should have an extension for it. So here's what we've got. So we've got, it goes through every line, and then it goes through every character on the line. And if that coordinate, so that XY position, matches the character passed into this function, then it calls our block with that coordinate so that you can then convert it to something. So basically what this is used for is, what we're going to do here is we're going to convert it to these blocks for the problem. Okay, next thing, I'm actually surprised this doesn't exist already on a set. I just made an extension so that you can give a set to another set and say, hey, take everything in this set, and if you've got any of them, remove them, or if you've got them, add them. So it's just a quick way to add and remove stuff from a set. And then I've got this, which is, again, it comes up so often, I just thought we should have a parser set up for it. It is character grid from a string. So you take a string like this, and it turns it into an array of characters. It's just a super common problem in Advent of Code, so I figured might as well have an extension for it. Okay, and then finally, an extension on any collection where you can do count where. And basically what this does is it goes through every item in the list, and it checks to see if something's true, and then it returns how many times that instance was true. And you'll see where this is valuable later. Okay, so let's just jump into the problem then. Okay, so you should notice right away Conway. If you're not familiar with Conway's Game of Life, go Google it right now. It's basically a set of rules so that every time the game iterates, these little things move across the screen in some direction, and there's all sorts of interesting problems and equations and things like that that people have come up with for Conway's Game of Life. So obviously that's what this is going to be about. Okay, you have a pocket dimension that contains an infinite three-dimensional grid at every integer three-dimensional coordinate, x, y, z. There exists a single cube which is either active or inactive. In the initial state of the pocket dimension, almost all cubes start inactive. So this is where the octothorpes and the points come in. And this down here is basically, it's spelling out, this is an active cube, this is an inactive cube. And our space. And then basically what we need is to run 6 cycles of Conway's Game of Life. Here are I actually don't know enough about Conway's Game of Life to know if these are the actual rules of Conway's Game of Life, or if this is their own rules that simulate the same thing. But basically, you go through all of them and you say, okay, a cube is active, and 2 or 3 of its neighbors are also active, then the cube can stay active. Otherwise, the cube becomes inactive. If a cube is inactive, but exactly 3 of its neighbors are active, the cube becomes active. So that's kind of the way that the cubes turn on and off. Now, so you might look at at a problem like this, so you can see how much sample input they give us. So you might look at something like this and be like, oh my gosh, okay, so I've got to keep track of all of these, but then it's an infinite 3D thing, so we have to keep track of all of them. But actually, because the rules all depend on the neighbors, you actually only have to keep track of each of the actives and then check the squares around them, because if they can only check their neighbors, that means that all of the growth can at most happen one in each direction for the cube. So that's what we're going to start with here. Okay, so let's jump into this. So let's start with part one. What is part one says? Run 6 times, right? Yeah, run 6 times. And then you should have 112 cubes left. So, given your initial configuration, simulate 6 cycles and then count how many cubes are active after the 6th cycle. Okay, so the first thing we want to do is we want to get our grid. And this is going to be input.characterGrid. So that's where our first extension is already coming in handy. And then the second thing we want to do is we're going to say, we want our active coordinates for each of the cubes. So we want to know which coordinates have an active cube in it. And we don't really care about the ordering of the list. So we're going to make this, a set. And then coordinate 3D is a class that I made that basically just has an X, Y, and a Z. It has the ability to offset itself, and it has the ability to tell you all of its neighbors. And you might think, holy cow, like how did you come up with that? Well, coming up with the neighbors is super simple. You just, for X, Y, and Z, you just go from -1 to 1, and you create a coordinate at each direction, and then that's all of its neighbors, with the only exception being the cube itself, because you can't be a neighbor to yourself. And that's it. Okay, so let's go back. So we're going to have a set of 3D coordinates, and we're going to make a set out of our grid, and then we're going to map. This is where our other thing comes in handy. So we're going to map this so that each coordinate in our 3D map is going to turn turn the coordinate 2D, because this is this starts as just some 2D coordinates in a grid. Xcode. I can't click anything. I can type. That's weird. X, Y, Z. There we go. $0.x, $0.y, and 0. So basically this just takes our 2D grid that is our input and turns them into 3D points. So nothing super fancy there. We need a closing parenthesis. Okay, so that will give us all our active coordinates. It'll turn this 2D little illustration into a set of coordinates, and then the next thing we need to do is we need to run 6 cycles of the game. So we're going to start with a loop that is, and we don't care about saving the index, 0 through 6. And then what we're going to do is we're going to basically run those full set of rules, and we're going to keep track of all of the coordinates that we need to add. So we run the rules and we found some new places that need to be added to it. We're going to keep track of all of them that need to be removed, and then we're going to apply that all at once. So we're going to go var2 add is a set of coordinate 3D. And to remove is a set of coordinate 3D. So we've got 2 sets there. These are their adds to removes. So we're going to start by doing the rule for active blocks. So the rule for active blocks was if a cube is active and exactly 2 or 3 of its neighbors are also active, the cube remains active. Okay. So we're going to go for each of our cubes, I guess. for each cube in our active coordinates. Is that what they're calling them, as cubes? Cubes? Yeah, all cubes. For each cube in active coordinates, we're going to say, we're going to count all of them that are active, or all of the active neighbors for each cube, because that determines whether it can stay active or not. So we're going to say cube dot all neighbors dot count, and we're going to say where active coordinates dot contains $0. So this will take all of the neighbors of a cube, and it will count the number of times it finds a cube that is in our active coordinates. So then if our active count does not equal 2 and our active count does not equal 3, then to remove dot insert $0, not $0, cube. There we go. Okay, so for each cube, we're going to count its neighbors that are actually already active, and then if it's not 2 or 3, then it has to become inactive, meaning we remove it from our active coordinates. Okay, now let's do the next part. So what we want to do next is we want to go through and we want to take all our inactive blocks and we want to see if they should be activated. So we're going to say neighbors, this is the neighbors of everything, and what we're going to do is we're going to say active coordinates dot reduce, and we're going to start with an empty list of coordinates, and we're going to say $0 plus $1 dot all neighbors. Oh, there we go. Okay, now the only risk of this is, so we start with an empty array, which is what $0 will be, is that starting empty array, and then $1 is going to be everything in our each coordinate in active coordinates, and we're going to take all of the neighbors from each one and we're going to stuff them all into this one big array. Now you could have duplicates in there, so what we're going to do is we're going to wrap this in a set so that we don't have any duplicates. Okay, so we're basically going to do the same thing again. So we're going to say for a cube in neighbors, and then the rule is if, what does it say? If it's a cube is inactive, but exactly 3 of its neighbors are active. Okay, so we're going to say let active. Well, actually, what we should do first of all is we only want inactive. So if one of the neighbors that we're visiting happens to be one that's already active, we want to skip it because we're only looking at inactive. Okay, so active count equals cube.all neighbors.count where active coordinates contains $0. So literally the same thing we did here. And then what we're going to do is if active count equals 3 to add dot insert cube. Okay, so that's how we do to add and to remove, and then after we have done that, this is the end of our cycle. We're going to say active coordinates dot remove all from, and we're going to say to remove, and then we're going to say active coordinates dot add all from to add. Okay, so this is the 2 rules that we have to do. This is applying those rules all at once, because if you remember, it says it's applied simultaneously, which means we can't update the collection as we do it. We have to come up with everything that needs to be done and apply it all at once. So that's why we can't mess with active coordinates as we're going. We have to save these off. Okay, so then the last thing is it wants us to submit the number of active cubes. So then what we're going to do is we're going to just say, okay, print active coordinates dot count, and so let's run it on our input here. Did I do it right? 286 at the end. Did we get that right? Examples, 286. Okay, so we did implement it correctly. All right, jump to part 2. Your simulated results don't match the experimental energy source integer's expectations. Okay, the pocket dimensions contain an infinite 4-dimensional grid. At every integer 4-dimensional coordinate space x, y, z, w, there exists a single cube, which is actually a hypercube, which is still either active or inactive. Okay, consider the number of active neighbors of each cube. For example, okay, big, long set of examples. Okay, this is literally the same problem, but they want it to be 4-dimensional. So I'm going to grab this, and just like we can create a coordinate 3D class or struct, it is super easy to create a coordinate 4D. Just adding a W on there, because we already had X, Y, Z. In this loop, adding a loop for W, adding a check for W, and then in our offset function, being able to offset W. That's it. Same problem. So then we're going to say Command Option F, coordinate 4D, and we're going to 3D, and we're going to replace it with 4D. Boop, 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 boop. That's it. Okay. Let's run part 2. We need a W there. And since it starts out as 2-dimensional, W is 0, the same way Z is 0. Okay, so we got 286 for the first part, just like we expected, and still running 960. And that's the correct answer. Okay. That's it. That's Conway's Game of Life. Hopefully you guys enjoyed this one. If you're really interested, Google Conway's Game of Life and also go check out the subreddit, which is reddit.com/r/adventofcode. There's a really cool thread where somebody was doing something like this, with this in Minecraft, which is pretty cool since it's a 3-dimensional simulation. Anyway, if you like these walkthroughs and these solves, go ahead and like and subscribe. We're going to be back on schedule starting tomorrow. And liking and subscribing both lets you get notified when we have a new episode, and it also helps us grow. So we appreciate it. We'll catch you next time. See ya.